Welcome to the CompTIA A plus 220 1101 or Core 1 exam. This is Objective 2.1 Internet Protocol. If you need to move a box from one place to the other, a common way to accomplish that is to get a moving truck. We can put boxes in the moving truck, move that box to another location, and unload the moving truck. In the case of networking, the road that we're driving on is the network. So if you've got a wireless network, a DSL network, a cable modem, or have an Ethernet switch, that is the road that we're using to transport this particular package. In this metaphor, the truck itself is what we will consider the Internet Protocol, or IP. We've designed all of these networks so all these types of trucks can move most efficiently between one point and another. And each moving truck is a box, and inside that box is your data. The moving truck has no idea what's inside of the box. All it knows is it has one job, which is to put that box in the back of the truck, transport it across the network, and unload the box on the other side. If you're able to open the box, there would be a certain type of information inside. It may be specific to an application or particular function on the network. You can think of the information in this box as belonging to a particular room in your house. So when the box is delivered, that box needs to be moved to the bathroom, to the kitchen, to the living room. This is the encapsulation process that tells us where it goes across the network. We would place that box inside of a truck. The truck would then move across the network to the other side. We remove the box from the truck, we open the box, and we take the application data out. So when network is moving across the data, it's not concerned with what kind of data it is, it's just where it's going. And after it has arrived, and then it will transport it to the correct place. If you were to look at this visually, this is the way that our network operates. On one side, you may have your device or a workstation, a client or a laptop computer, and on the other side is the server. This could be a web server, a mail server, or any type of server that you'd be connecting to. This client is going to send information to the server, and if this is across an Ethernet network, then everything inside of the Ethernet packet is what we call our Ethernet payload. In Ethernet, we also have a header at the beginning of this particular frame and an Ethernet trailer that's at the end of the frame. This Ethernet payload could have anything inside of it, but as you're probably aware, the most popular protocol we use on our network is the Internet Protocol, or IP. So our Ethernet payload will have an IP header, and then there will be an IP payload within that particular part of the frame. Obviously, the IP payload has information inside of it. This could be TCP data, this could be a TCP header, this could be a TCP payload. And as you probably can expect, that TCP payload can be separated into different types of data. So for the entire Ethernet frame, inside we have IP. Inside of IP we have TCP. Inside of TCP we have HTTP data. So it can be layered in different ways. Let's drill down into this IP packet at the TCP protocol and the UDP protocol. TCP and UDP are transported inside of that IP packet. We commonly say that they are encapsulated with IP, and they are two very common ways to move data from one part of the network to the other. You may be using TCP for some applications and UDP for other applications. You may also hear someone refer to TCP or UDP as operating at the transport layer of the OSI model. Sometimes refer to that as layer 4. You may think that IP is all you would need to be able to move across data from one network to the other. In many ways that would be correct. But TCP and UDP add additional capabilities that IP can't provide. For example, these provide multiplexing so that you may have different applications on your system communicating to separate servers all simultaneously. So your workstation is sending a lot of information for a lot of different applications to the server, and the server is able to determine what applications are in use through this use of multiplexing. Let's really break down the difference between TCP and UDP. TCP stands for Transmission Control Protocol. We often refer to this as a connection-oriented protocol. That's because there is a formal process to set up the flow from one device to the other and a formal process to tear down that flow when the conversation is over. We sometimes refer to TCP as reliable delivery. This doesn't mean that TCP somehow works better or faster than other protocols on the network. It means that TCP has a built-in system to ensure that data has been sent and has been verified as received. This allows us a number of different features behind the scenes. And one of the most important is that TCP can reorder messages that may have been received out of order, which sometimes can happen on networks that have multiple links in a single location. And TCP can manage a retransmission process so that any data not received by the destination can be corrected. TCP has also have flow control mechanisms so that it is a device that feels that it is receiving information too quickly. It can tell the other side to slow down and balance. UDP is the user datagram protocol. With TCP, we had a connection-oriented flow, but UDP is a connectionless flow. There's no formal process to set up a traffic flow, and there's no formal process to tear that down at the end. UDP simply sends data from one place to the other, and is very simple transmission to be able to send information across the network. Because there's no acknowledgement being sent by the destination device, we refer to UDP as unreliable. Again, that doesn't mean that UDP does not work as well as any other protocol in the network. It just means that there's no need for a recipient or any acknowledgement. If you compare these two protocols, it does sound like UDP is not as functional and therefore may not be the best choice for sending information over our network. But in reality, UDP plays a very important role in being able to send information very quickly over the network. UDP is most associated with real-time communication. Communication where you can't stop, retransmit information, and then catch up with yourself. If you're on a phone call, there's no way to rewind the conversation and send a packet that may have been missed a second or two ago. With UDP, we just send the data. So examples of protocols that use this are DHCP, which is the Dynamic Host Configuration Protocol. This is the protocol that we use to automatically assign IP addresses to our devices, and another protocol that uses UDP is TFTP, or the Trivial File Transfer Protocol, which uses UDP as its transport mechanism. Since both of these protocols are using UDP, information is simply sent across the network with no type of acknowledgement that the data was received on the other side. An example of protocols that take advantage of this return receipt functionality is HTTPS. That's the Hypertext Transfer Protocol Secure, commonly used to send information in our web browsers, and protocols like Secure Shell or SSH would provide us an encrypted form of terminal communication between our systems. If our HTTPS data between our web server and a client somehow loses a packet between point A and point B, TCP will recognize the packet missing and adjust it. So think of a network as a road, and all of these trucks are transporting boxes through the road, and they have a destination to go to. When the box is delivered, we have to determine the room that it's going to so it can receive the box. In the case of TCP and UDP, there's an additional piece of information that's added to all of those conversations, and that piece of information is a port number. That port number is That port number determines what room in the house it's going to, or in this case, the actual server or application on the server that it needs to address. The port's number written on the side of the box, and so when it arrives, you can figure out what app, what port, and what address it needs to go to. For example, we have a bedroom that's port 80, so that's where port 80 would go. We have a living room that's port 443. We have a bathroom that is port 25, and the kitchen is 123. So that's an example of how packets are delivered. So like we talked about, it's an information highway with all these roads and all these trucks moving around. There's so many addresses they could go to. There's so many ports that they could use, and there's so many applications that can receive the data. Non-ephemeral ports are ranging from 0 to 1023. These are the most commonly used ports, and we cannot customize or change them. However, ephemeral ports are 1024 up to 65,535. These ports we can use, and they're not actively used by any applications or protocols. Here are some common ports that we use and how it would be sent over the network. Common ports for a web server would be TCP over 80, VoIP servers, UDP over 5004, and email server, I guess that's like IMAP, TCP over 143. So in the bottom we can see there's a client and we have a server. So there's headers. You would have the IP address, destination, TCP, the protocol, and then the actual data that it needs to send with the trailer. And we are at the end of the IP protocol. Okay, pop quiz. What protocol is used to transfer data with integrity? A, UDP, B, TCP, C, SSH, or D, SSL? And the answer is TCP. TCP makes sure that all of the data is checked and that it sends correctly. So UDP does not do that. It is connectionless or stateless. Thanks for watching.